Hi there, and welcome to Chapter 1.5 from Stevens' Matrices, Vectors, and 3D Math. Here we're going to discuss a few items from vector spaces. In the last chapter we defined what a vector space was, and we showed you the standard bases for R2 and R3. And so we're going to eventually dive into more complicated bases, and so that's one of the topics in here. But we're going to talk about linear independence, span, basis, and dimension. All right, and so we're going to do a little refresher here first. When we talked about a linear combination of these vectors with these coefficients, a linear combination just looked like the first coefficient times the first vector plus the second coefficient times the second vector, on and on until you get to the last coefficient times the last vector. And that was a linear combination of those vectors, and that can be more easily expressed as this matrix multiplication, where that's your first vector, is the first column of M, second vector, on and on, last vector, and these are your coefficients. All right. And we showed that the standard basis for R2 had these two vectors, E1 and E2. By the way, when you put those into your M from this situation, it's actually 1, 0, 0, 1. It turns into the identity matrix. And likewise for R3, the standard basis consists of E1, E2, and E3. They have the same name, so you do have to know what vector space you're working in. Like in R2, this is E1, but in R3, this is E1. So you have to know the context in which you're speaking before you know exactly how many terms are in E1, E2, and E3. Right. But in any case, once you put them into matrix form, you'll always get the identity matrix. Okay, so we're going to start off with a preliminary definition of a basis, right? And it is the smallest collection of vectors that can be linearly combined to obtain any of the other vectors in that space. Right? We don't want just we don't want a basis to have more vectors than it needs. So we want this sort of minimal set, but we want to be able to hit every vector in the vector space as a linear combination of those vectors. Right? So to put that another way, including some terms that we haven't learned yet, it is any collection of linearly independent vectors from the space that span the entire space. Right? Okay, so here we go. Here we're going to talk about linear independence. All right, and we're going to give a couple of definitions. One is this intuitive definition, right? And so the way this starts, I'm going to go back up to here for a second. Suppose I have these vectors, v1, v2, up to vn. So I have n vectors, all right? And we talk about whether or not these vectors are linearly independent, right? So linear dependence, the intuitive definition. These vectors are said to be linearly dependent if at least one of them can be obtained as a linear combination of the others. In other words, one's sort of they're not really independent in the sense that you can get one of them as a linear combination of the others. It means that there is some vector, one of the vectors in there, can already be expressed as a linear combination of the others. Right? The formal definition, and so this intuitive definition should make a little more sense, right? It means that one of them is already sort of included as a linear combination of the others. So there's one that's not really independent. That one's not independent. Right? And so this set of vectors are called linearly dependent in that case. The formal definition means that you can obtain the zero vector as a linear combination of those vectors. And specifically, you can do this where at least one of these A's, and there could be more in there, is not zero, right? That is, you can take a linear combination, a non-zero linear combination, meaning that one of these has to be non-zero, and I can hit the zero vector, right? And if that's the case, then those vectors are called linearly dependent. If you can't do that, if the only combination that hits 0 is 0 v1 plus 0 v2 plus on and on plus 0 times the last one equals 0, if that's the only combination that hits the 0 vector, then the vectors are called linearly independent. And I'm going to do a little mini proof here, and here we'll go in both directions. Suppose we have the intuitive definition and we want to imply the formal definition. Well, here's the intuitive definition. It means that one of them can be expressed as a linear combination of the others. Well, if I just subtract vk from both sides, then I get the 0 vector over here, and I get a non-zero linear combination. The reason I know they're not all 0 is because the coefficient of vk is not 0, it's -1. Right? And that gives me the definition, the formal definition. Right? On the other hand, suppose I have the formal definition. It means I can get this 0 vector where one of these a's is not 0. And we will, for the sake of picking one, suppose a sub k is one of them that is not 0. Then I can subtract ak vk from both sides, and it shows up over here. And then I can divide by negative ak, because it's not 0, and I get vk is actually written as a linear combination of the others, and that's the intuitive definition. So they are actually identical definitions, just one is more favorable towards intuitive interpretation. Alright, so moving along. Determining linear independence, right? How do we determine? Because those definitions, one's intuitive, the other is the formal definition, neither one seem all that easy to use, right? But the thing is that second, the formal definition of linearly independent means that if I can hit this 0 vector with a non-linear combination, or a non-zero linear combination of my vectors, then those vectors are dependent, right? So what I do is, instead of writing my linear combination like this, I write it in matrix form. There's the first vector, second vector, on, nth vector. There's my coefficients. And I have to hit the 0 vector, the vector of all zeros, right? If this system has a non-zero solution, meaning one of these answers is not 0, one of these coefficients is not 0, then the vectors are independent. If the only solution is where all of them are 0, the vectors are linearly independent. All right. Okay, so here I'm going to do this. I'm going to do an example and show you how easy it is. It seems complicated. Once you do one, I promise it's a lot easier than you think. So here I have two vectors, v1, -1, 0, right there, and v2, 3, 4, right there. I want to determine whether or not these two vectors are linearly independent. So all I do is set up the equation m times a equals 0. The 0 vector, 0, 0. Right? And then I want to solve for a1 and a2. Well, if you look at this matrix M, the determinant of M is -1 times 4. So the determinant of M is -4. So by our super theorem, it means that M has an inverse. So the solution looks like A1, A2 is just equal to M inverse times 0, 0. But no matter what M inverse is, when you multiply it by the vector 0, 0, you get 0, 0. And that is the unique solution. So the only solution, the unique solution, is A1 equals 0 and A2 equals 0. That is the only solution. Therefore, these two vectors are linearly independent. Right? And you can actually use the linear, or not the linear, but the intuitive definition to figure this out too. If you only have two vectors, -1, 0, and 3, 4, the only way that one can be obtained as a linear combination is if one of them is a scalar multiple of the other. And what you can see here is that that's not the case. All right. But that intuitive definition really only works when you only have two vectors, and it reduces to one being a multiple of the other. So that's what this is here. The shortcut can only be used if there are only two vectors. Okay, so determining whether or not the vectors are linearly independent is really just a matter of putting them as the columns in a matrix and getting the determinant. All right. If the determinant is not 0, they're linearly independent. If the determinant is 0, then they are linearly dependent. Okay, so now let's talk about a span, right? That was part of our definition of a basis. Suppose I have these vectors, v1, v2, vn, up to n. They are said to span the vector space if every vector in the vector space can be written as a linear combination of them. What that means is that if you look at any vector in the vector space, any vector, right? Any vector, I can get that vector as a linear combination of these vectors. In other words, I can write x in this form, right? A linear combination of those vectors. So in practice, it's actually really easy. We're going to express this linear combination like this. And we're going to say any vector x can be written as a linear combination of those vectors. Right? So for example, let's take those same two vectors. I have the vector v1, -1, 0, and v2. Show that they span R2. That means we have to take a linear combination, v1, v2, and I have to be able to hit any vector. I can put anything in there. I need to be able to solve this. I need to be able to solve for a1 and a2 no matter what x1 and x2 are. And that seems complicated. You know, there's infinitely many things to check. There's infinitely many possible solutions here. There's infinitely many, well, let's put it this way. There's infinitely many x's out there that we would supposedly have to check. And that would result in, you know, infinitely many different solutions. So it seems like this extraordinary task would be impossible to prove, but it's really quite simple. Right? If you give me any x1 and x2, then a1, a2 is equal to m inverse times x1, x2. I don't actually care what x1 and x2 are. All I want to know is, does my m have an inverse? And it sure does, because the determinant of m is -0. It has an inverse. I get a unique solution. And so it doesn't matter what x1 and x2 are. I will be able to solve for a1 and a2, and I will be able to get that desired linear combination. What that says is these two vectors, -1, 0 and 3, 4, span R2. Right? Okay. So now we're going to get finally to our basis, right? Because eventually we're going to want to do a change of basis. So a basis is a finite set of vectors, right? That so that they are linearly independent and they span all of V. So that's all I need. If I get the vectors that are linearly independent and they span the entire vector space, then that set constitutes a basis for that vector space, right? And really, so you got to show linear independence, and you have to show that they span all of my vector space. But the thing is, we just showed how you do that. If you go for linear independence, it's setting up the matrix M that contains those vectors as columns. If you're looking for span, you set up the matrix M that has those vectors as columns. So getting both parts here, both parts is just a matter of looking at that matrix whose columns consist of my vectors that I'm worried about here. V1, V2, V1 is the first column. V2 is the second column, and then Vn is the last column. So I'm just going to be looking at that matrix, right? So if we set up that matrix M, if the determinant is 0, the vectors do not form a basis, right? Because not only are they linearly dependent, but they don't span the entire space. If the determinant is not 0, then I have a basis, right? So for example, for our last vectors v1 and v2, verify that those vectors form a basis in R2. Well, on the previous page, we demonstrated that they were linearly independent and that they span R2, so that proves that they form a basis, right? But if you just looked at that matrix M that has -1, 0, 3, 4, the determinant of that matrix is -4. So I really get all that for just by finding the determinant. So the determinant determines a whole lot, all right? In R3, prove that the vectors 3, 0, 0, 0, 2, 0, and 0, 0, 4 form a basis for R3. Super easy. There's V1, V2, V3. The determinant is 3 times 2 times 4. The determinant is 24. I have a basis. It's that simple. There's a lot going on in the in defining a basis, but when you set them up into matrix form, determining whether or not you have a basis is really quite simple. And by the way, with respect to this basis, all right, that's the first vector, second vector, third vector, then that radius vector of my ellipsoid from chapter 1.4, which was 3, 2, 4, that was the radius vector. This was the x radius, y radius, z radius. If you write that in terms of this basis, that's 1 times 3, 0, 0, plus 1 times 0, 2, 0, plus 1 times 0, 0, 4. So with this as our basis, the radius vector is just 1, 1, 1. And my ellipsoid has become a unit sphere. I know it seems crazy, right? The radius vector in the new basis is 1 in the x direction, 1 in the y direction, 1 in the z direction. I'm set. I have a unit sphere. Amazing. And we'll actually do this in practice in the next chapter. So now that we have a basis, we can actually define what the dimension is. And the dimension of a vector space is the number of vectors in every basis. All right, every basis will have the same number of vectors. So if you find a basis, figure out however many vectors are in there. That defines the dimension. All right. So for example, verify that the vector space R2 has dimension 2. Well, we figured out that V1 and V2 form a basis. There's 2 of them, so the dimension of R2 is 2. And you probably would have guessed that without all of this formal vector space definition and linear combinations. All right. Another example, in R3, I claimed that E1, E2, and E3 formed a basis for R3. That was way back. That was a couple sections ago, where E1 was 1, 0, 0, E2 was 0, 1, 0, and E3 was 0, 0, 1. I said this is the standard basis, right? So now it's pretty easy to confirm that that is indeed a basis, and it's much easier than you think, right? So the first thing I want to demonstrate is that they are linearly independent. I need to show that they span R3. I need to show that they determine a base. They form a basis for R3, and verify that the dimension of R3 is 3. It's all done in one determinant calculation. There's E1, E2, E3. Put them in a matrix. The determinant of M is 1, but specifically it's not 0. That means these vectors are linearly independent. It means that they span R3. It means that they form a basis for R3, which in turn tells me that the dimension of R3 is 3. Right? And it's all from just getting the determinant of a matrix. Great stuff. And so the dimension of R3 is 3, again, as you probably would have guessed. All right, so that brings us to our super theorem version 2. And super theorem version 1 had these first 4 to begin with. All right. So all we do is get a few more treats in here. With the following are equivalent. All right. And we'll start off with the determinant of A not being a 0. But if you get any of these, you get all of them. That's what we mean by the following are equivalent. If the determinant of the matrix, of a matrix A, and this is a square matrix, n by n, if that determinant is not 0, then I give it a unique solution for any matrix equation of this form. The matrix has an inverse. It is row equivalent to the identity matrix. So we had those in version 1, but now we also know the columns are linearly independent, the columns span Rn, and the columns form a basis for Rn. Right, so all of these, so if you get any of these, you get the remainder. Usually we start with this one. We get the matrix, we take its determinant. If it's not 0, we get all of this for free. If it is 0, all of that goes away. Again, the determinant. It determines a lot of things. Okay, so let's see some examples of our super theorem. In each of these examples, you're given a set of vectors in R3. Determine if they form basis for R3. Comment on linear independence or whether or not they span R3. So here's my first set, V1, V2, V3. We set it up in a matrix, V1, V2, V3. It takes a little bit of work. You can either do an expansion across one row, any row or column, or you can plug this into MATLAB. It looks like I expanded across my first column. So it's 1 times the determinant of this matrix, which is 0 minus 2. So 1, 0 plus 2. And then going to the next one, that's 2. It's actually negative 2 because it's negative 1 to the row plus column, or 1 plus 2, so it's negative 1 to the third, so that gives me negative. So there's my negative. Negative 2 times the determinant of this matrix, which is negative 1 times 5 minus negative 2 times 2. All right. And then my last term in the cofactor expansion is 1, technically times negative 1 to the 1 plus 3, but that's negative 1 to the 4, so it's positive, times the determinant of this matrix, which is negative 1 minus 0. And when you do that, you get a determinant of 3. Most importantly, that determinant is not 0, so the vectors are linearly independent. They do span R3, and they form a basis. See how much you get? You get an awful lot for nothing there. Well, not for nothing. You do have to figure out that determinant. Suppose you were to look at these 3 vectors. V1, well, here they are. V1, V2, V3, we put them in that matrix. Check the determinant. So it's going to be 1 times the determinant of this matrix. So that's 0 minus negative 2, which is 0 plus 2. And it's a 2 times negative 1 to the 1 plus 2, negative 1 to the 3, so I get that negative, times the determinant of this matrix, so that's negative 5 minus negative 4, plus 4 times the determinant of this matrix, which is negative 1 minus 0. And when you carry that out, you get a determinant of 0. So that's the other situation, right? So we know the vectors are not linearly independent. They are linearly dependent. They do not span R3, and they do not form a basis. And what you may have noticed, but probably didn't, is that if U3 can actually be obtained as a linear combination of U1 and U2. For example, if you take 2 times U1 and add it to 1 times U2, you'll actually get U3. Right? So you get 2 plus 2 is 4, negative 2 plus 0 is negative 2, 4 plus 1 is 5. So they're not linearly independent, right? The determinant is 0. They don't span the space. They don't form a basis. All right, so now I only have 2. Is this a basis for R3? Well, certainly not, because there's only 2 of them, right? And if I put them in a matrix, 1, -1, 2, 2, 0, 1, I can't use the super theorem, because the super theorem, the matrix has to be square, right? So the super theorem is out. However, we know that the basis for R3 must have 3 vectors, so that we certainly do not have a basis. And so that means they're either linearly dependent or do not span R3. Now, since there's only 2 of them, you can actually see that they are not linearly independent, because in the case of only 2 vectors, linearly dependent means one's a multiple of the other, and that's clearly not the case. So they are linearly independent, but so they're not going to span, they can't possibly span R3, right? You're not going to span a 3-dimensional space with 2 vectors, right? So not a basis, linearly independent, they don't span R3. For number 4, I actually have too many vectors. I have 4 vectors, all right? And right away, if I ask, is this a basis for R3? Right away, you know the answer is no, because we found a basis for R3. It had 3 elements, so the dimension is 3, and any basis will have 3 terms. So we don't have a basis. We know that for sure. All right? You can't really use the super theorem, because if you put these into a matrix, you'd have a 3 by 4. So it's not square. So you can't use the super theorem, right? That's out. So these either don't span R3 or they are not linearly independent. Now, it's hard to tell, and if this was a bigger course in linear algebra, you'd get into the concept of rank and nullity, and we could figure out exactly what the case was here. But more than likely, I have 4 vectors. More than likely, these do span all of R3. I got a surplus of vectors. More than likely, one of them can be obtained as a linear combination of the other 3. In other words, they're probably not linearly independent. And to go through that, you have to go through, to fully figure all this out, you really have to start working with non-square matrices, getting the rank and the nullity and the dimensions of the null space. And it gets a little tricky, and it's more than I want to get into in this book. But a good guess is that there's too many vectors to be a basis. They are probably not linearly independent, right? Well, they can't be linearly independent, because otherwise they could form a basis, right? So they're not linearly independent, and they probably do span R3. But to figure all that out, I mean, there's a chance that they don't span R3, right? If these were just scalar multiples of the same vector, you would not span. So making that determination takes a little more in-depth study of linear algebra, and we're not going to get into that right now. But you can tell you have too many, so you certainly don't have a basis. All right. Oh, that brings us to the problem set. All right, so that wraps up Chapter 1.5. I will see you in Chapter 1.6. Bye.